When we design a crushing and screening circuit, we expect like pure engineering precision. You run the flow sheets, you balance the mass, and it all looks perfectly clean on paper.
Right, yeah. You expect these highly predictable outcomes. I mean, it's highly controlled in theory.
Exactly. But then you step out into the actual plant, look down at a vibrating screen, and well, suddenly that precision just goes right out the window. Welcome, fellow mining engineers, to today's deep dive.
Yeah, it really turns into an ongoing battle with physics, honestly.
It really does. So our mission today is to build an operational playbook for optimal screen sizing. We are drawing directly from the MEKA handbook for this.
Yeah.
Because, the actual cost of the wrong specifications is just massive.
Oh, absolutely. It's a very delicate balance. If you specify a mesh that's too tight, you get blinding.
Right. The near-size particles just wedge right into the wire.
Exactly. And your open area drops to near zero. So your plant capacity just bottlenecks immediately.
But, if you go too wide, you get oblique particles slipping through. That means oversized passing, a contaminated product stockpile, and a highly costly rescreening process. You were basically punished for missing in either direction.
Yeah, you really are.
On this slide, we have to start with a foundational metric, which is the open area ratio. Think of this as like the breathing room of your screen deck.
Yeah, mathematically, it's just a ratio. It's the area of the open hole divided by the total area of the hole plus the wire itself.
Right. So let's unpack this a bit. What does that percentage actually mean for the plant?
Well, if we connect this to the bigger picture, it's all about throughput. Capacity scales almost linearly with this ratio.
Oh, really? Almost linearly?
Yeah, pretty much. A deck with 50% open area will process roughly twice the tons per hour of a 25% deck before overloading. I mean, it physically dictates how much material can fall through per second.
Wow, okay. Moving to the next slide. If we need to maximize that open area, how do we actually target the cut size? The handbook introduces the 80% rule here.
Right, the 80% rule. So basically, your opening size should be about 20 to 25% larger than your target D50.
And here's where it gets really interesting and honestly a bit counterintuitive. If we need a specific D50 separation, why size the opening that much larger? Doesn't that mathematically guarantee oversized contamination?
On paper, yeah, you would absolutely think so. But in the mechanical reality of a vibrating screen, woven wire actually deflects under heavy load.
Ah, okay. The wire itself is physically moving.
Exactly. Plus, particles don't just present perfectly straight down, They come in at oblique angles or they bridge together interacting with the fines.
They kind of clump up on the deck.
Yeah, exactly. So if you size the opening exactly to your target cut, going tighter just guarantees choking. That extra clearance isn't a mistake. It's an operational necessity to keep the bed fluid.
That makes total sense. Moving to the next slide, that brings up a physical problem. To keep that opening wide and fluid, you have to make decisions about the thickness of the wire itself.
Right. You are looking at a serious capacity versus durability trade-off here.
Yeah, so take a 25 by 25 millimeter opening, for example. If you use a thin 4 millimeter wire, you get a massive 74% open area.
Which sounds great for your throughput.
Right. But bump that up to a beefy 8 millimeter wire, and your open area drops to 57%. So what's the right call there?
Well, the governing engineering rule here is simple. Always select the thickest wire that still meets your baseline plant TPH targets.
Really? You sacrifice the throughput?
Yes, because the downstream savings you get from durability and drastically reduced changeouts almost always outweigh that marginal loss in sheer throughput.
Okay, that is a solid rule of thumb. On this slide, we've got the metallurgy matrix, we have the thickness sorted, but what about what the wire is actually made of?
Right, well, carbon steel is the universal default.
Yeah, but I have to ask, when do the actual economics justify upgrading to something exotic, like high-manganese or polyurethane?
Oh, that's fascinating. It's really how the environment dictates the chemistry. High-manganese actually work-hardens under impact.
Wait, it gets harder the more you hit it?
Exactly. So if you are crushing hard rock like basalt, it lasts 3 to 5 times longer than standard carbon steel.
Wow. And what about polyurethane?
Polyurethane drops plant noise by 5 to 10 decibels, which is huge for safety, and it provides an order of magnitude lifespan increase in high blinding zones.
But doesn't it cost like 2 to 4 times as much initially?
It does, yeah. But the elimination of downtime offsets that initial cost incredibly fast.
Oh, that is wild. Moving to the next slide, we shift to structural integrity.
Yeah.
Because, it doesn't matter if your mesh is made of space-age polyurethane if the frame holding it together vibrates itself to pieces.
Absolutely. A perfect mesh specification is totally useless if the dynamic load transfer fails.
Right. And the handbook specifically contrasts to German D-Ein pipe standards here.
Yeah. First, you have D-Ein Core 440, which is a standard wall pipe that is used strictly for non-load-bearing elements.
Like gust covers, right.
Exactly, just dust covers. Then you have D-Ein 2441, that's heavy wall, and it is strictly for primary cross members carrying the screen mass.
So if you mess that up.
Well, specifying 2440, where 2441 is required, basically guarantees structural fatigue.
Oh, man.
Yeah, and eventually catastrophic frame failure.
That is a disaster you definitely want to avoid out in the field. So we've talked about open area, wire thickness, metallurgy, and structural pipes.
Right. It's a lot of variables to manage.
It is. But the handbook states something really specific here. It says it requires exactly 3 documented changeouts, logging both hours and tonnage to establish an accurate life cycle costing baseline for any of these decisions.
Yeah, and this raises an important question for you, the engineer listening right now. When you pull a torn deck, are you actually documenting the hours and tons?
Or are you just throwing it away?
Right, exactly.
Think about it. How much invaluable empirical data is your own plant currently throwing in the scrap bin at every single maintenance shutdown? Don't miss the chance to turn that plant floor guesswork back into pure engineering precision.